The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to the webinar. Good day to all of you from across the world. This is the AISI webinar on design of a 4-span continuous Z-Purlin line supporting a standing seam roof. It's presented by Chris Moen, PhD in PE. Chris Moen is an enthusiastic engineer, an entrepreneur, a researcher, and an educator with interest and expertise in thin-walled structures, structural simulation, structural testing, and design of materials and systems. He's been doing this for many years. I've known Chris through my work with him on AISI committees, and he is quite the innovator in the industry. A couple of housekeeping items before Chris starts. Right now, everybody is on mute, but in the box off to probably the right of your screen, you've got a dashboard, and in that dashboard, there are handouts. These are PDF files. If for some reason you're not able to click on and download those handouts, please feel free to send an email to Dr. Helen Chen, who is also on the line, hchen, C-H-E-N, @steel.org, and she can get these to you. But for most people, if you just click on that link, you can get the handouts and be able to peruse through the slides at your own pace. In addition, this webinar is being recorded. So if there are other colleagues that were not able to be with us live here today, then you can ask for a link to the recording and watch this at your leisure. However, one of the benefits of being here on the live presentation is your ability to ask questions of the presenter. So during the presentation, there is a box on the side also for questions. You click on that box, you can type in questions, and we'll do our best to answer you. While Chris is giving his presentation, you'll have myself, Don Allen of Super Stud Building Products, Jay Larson, also with AISI, and Helen Chin with AISI, standing by to answer your questions. There will also be breaks during the presentations when we will pass on the questions that we can't answer directly to Dr. Moen. So without further ado, Dr. Chris Moen, welcome, Chris.
Thanks a lot, Don. Thanks for the introduction. And thanks to everyone for joining on this Friday afternoon. Today we're going to be going through an example, a calculation example of a 4-span continuous Purlin line supporting a standing seam roof. This is a project that has been going on for probably maybe over a year now, and it's been really quite enjoyable. I'd like to acknowledge actually AISI and especially the task group who worked with me all the way along, giving me great comments. So this example will be a little bit different than the traditional example because it will be run in a live notebook on the web, and so you have access to that. We sent out the link before, and I understand some of you may be having problems with that link, and so I can clarify that in a little bit when we get into the workbook. But yeah, so welcome everyone, and let's get going. I mean, this is what we're talking about: a roof, a roof on a metal building, and a standing seam roof. And this roof looks quite beautiful, I would say. Like we're all used to looking at these kinds of roofs when we drive around, or when we're designing them, or some of you are maybe getting on top of them sometimes when we're building them. And I think the public doesn't really doesn't realize how complicated they are to actually design from a structural perspective. Underneath the roof are these structural submembers, purlins, that span between frames, and those purlins are typically Z sections, singly symmetric. And the standing seam roof is connected with clips, and those clips are spaced at a certain, are spaced certain distance along the purlin, The purlin can be multiple spans. The connection point on the purlin is eccentric to the shear center of the cross section. There are gravity loads or uplift loads. The roof can have a slope. There can be splices over the supports for the purlin. And I mean, I could just go on, and it adds up to be like a long list, and it ends up being a very challenging structural problem that many people have been studying over the years. So the goal here today is to try to take all of that and consider everything that I've talked about today within the framework of the AISI specification, and do it in like maybe a little bit more of an automated fashion that makes things easier, makes things, I would say, simpler, and also because we're considering all of these different variables, we can also get some pretty interesting insight. And so we'll talk, and I'll share that with you today. So as I mentioned, like, we're working within the AISI S100 framework, and we're allowed to do that with what we would call, this is called rational analysis or calculation-based design. In 2016, there was a new section introduced into the I6 for metal roof and wall systems. And you can see it here at the bottom, I6.1, just member strength, general cross sections, and system connectivity. This work was a culmination of, or this edition was a culmination of maybe 5 years of MBMA supported research. The basic idea was to try, let's try to provide an alternative to testing, because really all we had up to this point was base testing, vacuum box testing, and could we really get close to calculating the capacity, considering all of those parameters I mentioned previously, by considering all of the connectivity of the purlin to the roof, and considering all of these important limit states that most of you have heard about, especially if you're working in cold form steel, especially local buckling and distortional buckling is very common in these types of thin walled open cross sections. So we're setting up the example to work within this framework of considering the connectivity of the purlin to the roof sheathing or the roof panels, and considering that as kind of a system. And this is like maybe a little bit, now we're getting a little bit deeper now, right? So we were looking at the whole roof, and it was really looking very nice, and now we're like down into getting into some of the nitty-gritty details where we have this purlin. There are actually, in this example, there are two different thicknesses of purlin that are considered in the 4 spans. And what we're trying to do is, like, I have a picture of a standing seam clip here. The clip is screwed to the top flange. And what we're trying to do is we're trying to consider calculate the demand loads on the purlin, and also consider on the capacity side, consider the influence of this clip. And like, for those of you who work in this industry, like, there are many different varieties, flavors, heights of clips. There's tall clips, low clips, there's fixed clips, there's sliding clips. And so today we've set the example up to be pretty general, and so that in the future we can include the stiffnesses associated with the specific clip that maybe you're dealing with. And the clip provides, we consider that the clip provides both rotational stiffness and translational stiffness to the flange that it's connected to. So you can see the clip here, and then you see that we have 2 springs that represent how this is, how the clip is interacting with the purlin. So now I'll just take it one little step deeper, and I would say the core piece of this analysis in this example is doing a second order structural analysis of the purlin line. And how do we do that? Like we have some tools to help approximate that. Like if some of you have worked with Mastan 2, which is an excellent program, both used in the educational world and in academics for teaching. We all use it for teaching. It can also be used in design. The current version of Mastan does not necessarily consider all of the effects that we have here, where like the Mastan is more set up for doubly symmetric sections, like an I section. And so putting in a Z, like with considering the load, like let's say the load is coming in here from the roof, like we needed something maybe a little bit more representative of this situation. And so we wrote down some equations recently, and that was part of this project. We're motivated by this AISI project, was to write down these equations, and these are just equilibrium equations for every little segment along the purlin. And you can think of it as like equilibrium in the bending in the about the x-axis, bending about the y-axis, and torsion. There's the reason that it's second order is because this represents equilibrium in the deformed configuration. So you see here there's like a U, which means that the purlin has displaced in the U direction, and there's some phi's. So like phi is the rotation. So the purlin wants to twist in the purlin line, and so like all of that is considered, and yeah. So like this is, I would say, one of the key new pieces it's integrated into the example that we're going to go through. Yeah. So maybe I'll stop here and ask if there are any comments or questions so far. I'm going to try to stop every 15 minutes or so. But so far I've just kind of introduced where we're headed, and now after this we'll get into the example. So are any questions so far about anything?
Chris, I haven't seen any questions typed into the question box.
Okay.
Just a reminder to participants, your microphones are muted, so if you talk, we can't necessarily hear you, but if you type it in the question box during these times when Chris pauses, we'll make sure and ask him those questions. If there's a specific diagram, oh wait, we just got one. Okay, well, so someone commented that there are slight differences between what you're showing on the screen and what the handouts show. But I guess we're getting more of a bonus on the screen, right, Chris?
There is this. It's always a bonus on the screen. You're right, Don.
All right. Well, I think you go ahead and continue, and as we get more questions, we'll ask them during the next pause.
Okay. All right.
Just a second, Chris.
Oh, yes.
Another question?
Yes, yes.
About the equilibrium equations?
Yes.
The question is, do any of the equations contain anything about vertical displacement? So
yes. So the vertical displacement is V here, and there's a V term in here and a V term here. So this is yep.
Perhaps the question is about whether there's any spring resistance required for the vertical.
Oh, so there is no spring included for the vertical component. It's a great question, and we we often think about that. Like I think that's in the sheathing brace design work that Ben Shaver has done. Like, I think that's considered or called the composite stiffness. That's not currently considered here.
Okay, and we have one more question. How is stiffness of attached bridging represented? I think the answer is simply that you have the rotational and translational springs that represent the stiffness of the, I'm sorry, this is for the bridging.
Bridging. Yep. So in this, that's yep. So they're talking about intermediate bridging between purlins, correct?
That's my assumption, yes.
Yeah. So in this example, that is not considered. So in the original examples that are in the AISI D100 manual, that intermediate bridging was not included, and so I followed that same trend. You'll see in a little bit when I talk about the Nextjournal, when I go to the actual live workbook, that intermediate bridging can be included but it was not part of the project.
Okay, I think that answers that.
All right.
By the way, the other voice you heard is Bob Glaus. Many of you know Bob from RSG Software as well as AISI committee work. Bob has graciously helped us out today, so you'll be hearing his voice during the webinar. And he also has an upcoming webinar with CFSCI. We'll talk more about that later. All right, back to you, Fred.
Sure. All right, so let's jump to this calculation notebook. This one happens to be Nextjournal, but you may have heard of Jupyter or others that allow you to perform calculations and write code in Python or other languages, other open source languages. So I wanted to make sure that everyone can access this. So I think in the email there may have been an edit added on the end of the URL. So if you can't access this, just delete the edit, and maybe Helen, I think Helen may have sent out a revised link, or if not, you can look in the chat window. But yeah, I just anyway, you'll be able to follow along here, but I just wanted to clarify that. All right, so I've written most of the details of the example here, and it just goes through step by step. Maybe I'll focus a little bit on how to use this notebook. Like, I'll just draw your attention to this, like so you can make a copy of this notebook and play with it yourself, so you can run it. The way that this works is that this notebook this web interface is connected to a computer, so every time you press the run button, you get assigned a computer, and that computer runs this locally and then brings it back onto the web. And so you can make a copy of this and put it on your own little temporary computer and run it and even change the variables. The source code for this, most of it, or at least the core part of it, was developed for this project, or was motivated by this project. And the software package that we're using is structureskit.jl, and I sent you a link to it. It's hosted on GitHub, and so there's some information here on how to, like, the usage and installation, and then it's organized into building blocks. And right now we just have a few building blocks here, but all of these are used in this example. So this plout beam, for example, like if we click here, this is the solution of those differential equations that I showed you earlier, and it gives some examples of how you can consider any general cross-section and what might be the dimensions that you're considering. You can consider, actually, I forgot to mention, you can consider loads in both directions. And then I provide an example here of how to run it. I'll just say a little bit more. I would say that this is one of the, so the solution of the differential equations, that is one of the innovations, I would say, and the benefits of using the open source software platforms. I'm using the Julia language, and in the Julia language, which came out of MIT about 10 years ago, and it's becoming very popular now, it has some really nice ODE solvers. So you can take that system of ODEs and put it and solve it, and solve them very quickly. And that's a little bit different than the traditional matrix structural analysis that we're accustomed to performing. So instead of developing the K matrix and inverting it and finding the displacements and internal forces, you can solve the system of equations by breaking up the Purlin line into little segments and then solving it directly from the differential equations. So yeah, that's maybe about all I'll talk about there. I don't want to get you too bogged down there, but that is one of the maybe unique parts of this work. All right, so source code, and we do some things like we have to tell the notebook we're using structures kit, and we're also going to be plotting some stuff, and I just list out the design specification, and there's an option to use allowable stress or LRFD to find the units. And then this is the example like that came directly from D100, and for the person who was asking about the bridging, it's a great question, and we've talked about it a lot. We just didn't include it here. The span layout is provided here, and you'll notice there are some little cantilevers on the end, which make this structural analysis a little challenging, and also that these splices, like there are these overlapping splices of the supports of the Purlin line, and also the Z's are changing from a 0.07 to 0.059. Yeah, so now and what we can do is we want to run a structural analysis of this, considering all of the load eccentricity and the connectivity to the standing seam roof. And so we get started by just defining and discretizing the member, just like you would do in a program like MassDan2. You define nodes and elements. Here, what we do is you just what I did. You have many options, ways of discretizing, but what I did was I just took like this segment and I said, all right, this is a piece, then this is a piece here, then this splice is a piece, and then this part is a piece, and then this splice is a piece, and like just broke it up like this. So there's maybe like 8 segments total along the length of the Purlin line. You can see here there's the 1 times 12, 22.5. Like these are just the distances along the length, and this is defining the section properties which are considered below. And there's 4 section properties. There's 1 material property, so it's always steel, but you could change the material properties if you wanted to. There are load eccentricity, load location, bracing properties, and cross-section dimensions. So all of these, like for each one of the chunks of elements, you define what the properties of each section of your structural analysis. This is a very similar way of doing it compared to when compared to any structural analysis program. All right, so now let's. So this example is set up not so much for pattern loadings, although pattern loadings can be considered in this type of framework. This is more like a simulated test, I would say. So we're considering first a gravity load. So we're pressing down on the roof and we're trying to see how much pressure the roof can take before a Purlin fails. And then we consider an uplift loading, where again you add a uplift loading, you increase the uplift loading until the Purlin fails. Like that is what we're doing here in this example. Define the Purlin spacing, and in this example, I've defined the roof slope as 1 on 12, which is It's a very common roof slope in metal buildings. Define the support and boundary conditions. So these are just like, so there are 1, 2, 3, 4, 5 supports. And if we go up here, there's 1, 2, 3, 4, 5 supports. So just denoting where the supports are, and also we give some information about that far end boundary conditions. In this case, consider them as free end cantilevers, according to the example. All right, so then Purlin section properties, we define them here, and so it's all the stuff that you're used to looking at for these types of singly symmetric or point symmetric sections, I's and an IXY, which is helps to define the principal axes, and J, CW. Omega N is for calculating the torsion capacity. Or WN, it's like the unit warping stress on the cross section. And then the local buckling, the critical elastic local buckling moments in the X and Y axis. So these are defined as the section properties. I've included some notes down here because there's a few like a couple tricky things, and yeah, I won't get too much into this, but I mean, there's some tricky things that we'll see later, like that the current AISI interaction equations are the ones that we're thinking about, that have been talked about in recent meetings, are maybe conservative, maybe not, and so like I don't know, I've multiplied omega n by 4 here because things were honestly, like the results were not making sense. So I'll talk more about that later. The critical elastic buckling moments. So I'll just discuss this for a second. So I calculated these outside of this workbook in CUFSM, which is an elastic buckling finite strip program that's freely available. If you just Google it, you'll find it. So in the future, like in this type of software workflow, we could calculate that and there are some evolving open source packages like PyCUFSM, which is a Python version of CUFSM. I decided not to include it here because it was going to add another level of complexity, especially mingling 2 languages. So then we would have Python and Julia in this notebook, and that would make things a little complicated. But for sure, like local buckling could be calculated in this automated workflow. And this is the local buckling about the x-axis and the y-axis of the cross-section as defined here, so the x and the y. Yeah, the Purlin cross-section information. So we need this when we're calculating distortional buckling, and all of it is like pretty consistent with ends up being 4 cross sections that we're considering. So like there's this Z.070, and then there's like we're adding a 0.070 and a 0.059 together here, and then we have just the 0.059, and then we have 2 0.059s, and so you end up having 1, 2, 3, 4 different types of cross sections. Then you could include an arbitrary or like whatever many cross section types you wanted, and it's this 1, 2, 3, 4 matches up with the member definitions above here. So like you see here, there's a 1s and 3s and 2s and 4s, and that's just so each one of those is assigned to the member segments in the analysis. Yeah. So let me just get through. So in what we found in these analyses is that the load location really matters. And so typically in a lot of analyses and in a lot of structural analysis programs, we're always assuming that the load is applied here, but that's not the case. It's applied up here. And when the cross-section starts twisting, that becomes very important in the prediction of the displacements and also the internal forces in the Purlin line. And so like defining where the load is being applied is important, and that's AX and AY. And so this is AX and this is AY. Yeah, and then material properties. And I think let's see, maybe I'll make it through this system bracing details and then I'll take more questions since it's 1:30, I see. So the system bracing details. So we've, in the research community, we've been working on characterizing stiffness values for connections for a while now. And in this case, I have assumed here that the standing seam roof that we're considering, it has a trapezoidal profile, and the roof is attached with these low fixed clips at a spacing of 24 inches. And with this assumption, now we can go and refer to some of the recent testing and data that we have that we can use in this analysis. So for example, the rotational spring stiffness that I showed you earlier is provided in a report generated by Professor Seek and his students. And I can jump over to that now. It's available, and I provided the link here. And this, you can just look to see there was some testing done where it's like kind of like an F test if you're familiar with that, and you pull here and you measure the rotation and you can derive a rotational stiffness. And this table is provided in that report. And so we have some actual numbers, like, so this is T stands for trapezoidal, LF stands for low fixed, and there's some different variations here, but you can see here that like these numbers, they're, at least for the case that we're considering, are around like 0.1 kip inches per radian per inch. So you have the power, like, so you can either pull this type of data from existing reports, or if you're a roof manufacturer and you can set up your own tests and get your own values for this and use them in a framework like I'm showing now. And for translational stiffness, there is not really much, like, there's not much work out there on the lateral stiffness of standing seam roof clips. I refer to one study that I completed with my students back in 2012. We studied sliding clips, and so the stiffness is much lower than what I've considered here, maybe like 1/10 of what we've considered in this example. So there's, as I'm alluding to, like, I'm just saying that there's for sure more work to be done in nailing down exactly what, like, the KX and the KF could be to produce these strength predictions or that are consistent with the tests that we have performed in the industry for a long time. But we're getting close. We're almost there. Like we're at, like, if you think of like an arch bridge, like the two pieces are meeting, and like we're almost there where like they're about to join, and then everything is going to be amazing, because like then the arch is going to stand up. I don't know if it's a good analogy or not, but we're very close to tying everything together. And so one assumption that I made for the lateral stiffness, or that we made here, is that for the lateral stiffness is twice that of the uplift. So the lateral stiffness for gravity loads is twice that of uplift loading. And so if you've done pressure box tests of these standing seam roofs, you know that like there's hugging for gravity loads, but that hugging doesn't necessarily exist for uplift loads. And so I found it reasonable to not use the same stiffness for both. I'll also comment here on the roof diaphragm shear stiffness. Like, so here we've assumed that the roof diaphragm shear stiffness is much higher than the lateral clip stiffness. there are ways of considering that, and there's recent research out there that has standing seam roof diaphragm stiffness in them, and like that I've included the link here. And so that could also be considered, is the flexibility of the roof diaphragm itself. In my experience, from what I've seen in tests and also in real buildings, the clips are the most flexible. They're much more flexible than the roof diaphragm. But yeah, so let me, so that gets us through the setup for the example. And so I'm happy to take more questions now for a few minutes.
So Chris, I just want to clarify to all the attendees that there is a link in the chat box that will bring up this example that you're showing in Nextjournal, and that since this is not in the PDF handout, you might want to bring this up and follow along as Chris is presenting. Let's see, Chris, we have another question here.
Okay.
And I think that was answered though during the presentation. It was about the sliding clips.
Okay. Let me just repeat it just to make sure we've got it answered. Okay. So did you test the stiffness of sliding clips under load?
Yes, that was the those are the tests. There haven't been much on, actually. I think Professor Seek, there are let me see here. S stands for sliding. So there are sliding clips tested for rotational stiffness, but the lateral stiffness, the KX, was not considered here. In this report, in these reports that where links are provided, also they considered sliding clips like the one, exactly like the one I showed here. This is actually from that experimental program. We characterize the lateral stiffness of the KX of this clip.
All right, thank you, Chris. That's all the questions for now.
All right. Okay, so we have the roof slope, we have like the geometry, we have the connectivity considered, we have all of it, and now it's time to run these. We can call them simulated tests. And so let's determine the roof capacity under a gravity load. And first, maybe it's useful to just look at the deflections. And so I put this in here just for you all to get accustomed to what the Purlin wants to do when it's loaded under in a gravity situation. I picked an arbitrary load of 10 PSF, and that's just so I could do it in Uplift, and so you could compare Uplift and gravity cases, like you can see the difference. And this is the setup, like a more detailed setup now. So like the standing seam roof is attached, we have the roof clip, and it's at a slope of 1/12, and we're gonna press down on this. We're gonna push this down. And what happens? So I run that. So this is just a call to a function here that runs that analysis and calculates the deflection. So you see here, it's U, V, and theta are just the lateral deflection, the vertical deflection, and the twist of the Purlin. And this is the first plot that we get. This is the first results that we get. This is along the Z-Purlin, so along the line here. You can see that like there are 0 points at the supports. This is the lateral deformation, U. So this is, so the Purlin, as we're pressing down, the Purlin is moving in this direction, in the U direction. And you can see here you can see here that I've also shown the discretization. So each one of these points is a calculation point for that ODE solver that I was talking about earlier. So this is user input, and so obviously if you use less points, you get a less accurate solution. And so this worked just fine for me and is pretty quick. It just takes a few seconds to run. One thing that we should consider here is that, so you can see these bumps. Like this is something I would say that's new for us. Like when we're thinking about this type of problem, like we've seen this in experiments. So if you run experiments, you can see this kind of stuff. But like this type of behavior is because we have the connectivity to the roof. So you can imagine like the roof, the purlin wants to go sideways, but it's being held back by the springs. And it's being held back by the springs, and it's being held back by the springs, and it's being held back by the springs. And so we see that behavior here in the lateral displacement. The numbers are very small here, so like I wouldn't get too excited about them. Like you can see overall that you can also see that the connectivity that we've considered is not allowing much motion. We can then get the vertical deflection. In this case, for 10 PSF, the purlin deflects about like 3/4 of an inch maximum at the end span. And we can get the twist. So we can get the twist all the way along the span. And the twist gets up to maybe about like 1/10 of a degree. You can also see here that there are jumps. So this is the change. So these jumps here are the change in stiffness, like from at the splice locations, and the calculation picks that up. Like that's another nice thing about, I mean, so you can do that in, of course, using beam elements in a structural analysis, but you can also get them here by solving the ODE system of ODEs directly. And so each segment that we were considering so pretty much here, like each point can have like a different E, a different I, a different whatever. And it's the solution, the solution that satisfies the equilibrium equations that all along the member is determined with solvers that were written by people who developed the Julia language. All right. Anyway, it's like, so the cool thing about like, so if you think back to like your undergraduate education, you remember that that you get internal forces, you calculate the internal forces from the displacements, from the derivatives of the displacements. And because of the fact that we have like, we can numerically calculate derivatives very easily with existing tools, we can easily calculate all of the moments, shears, torsion, and even bi-moment, which is like related to torsion. All of these things, the internal forces that we need, we can calculate them just immediately from the displacements. I provided so this is like just a general beam, and if you have a cut in a beam, and then you have like these are the internal forces, the positive internal forces on the beam. Like this is a way to guide you through the signs here. So the right hand rule, you remember like you're taking your right hand and sticking your thumb up in the air to follow the double arrows. Like that's what's going on here. So like the positive moment, you can figure out what the positive moment is physically by using your right hand and your thumb. And so like so we can just go through the moments here now. Like we can look at the moments for, this is still for 10 PSF, and yeah, we get the moments, and this looks like a typical moment diagram, right? Like this is nothing too exciting. We can get the shear diagram. So this is Vy, so the typical Vy that we're used to. But because we have a slope, well, because we have a singly symmetric cross section, and because also we have a slope, like I'll go back up here, like we have a component, for gravity case, we have a component of the load in this direction. And so there, all of that is considered here. And so like when we plot the shear in the other direction and the bending in the other direction, we get some stuff. This is maybe sometimes not looked at or considered, but it's definitely interesting. And again, you can see here, like in the weak axis bending of the Purlin, let's say, like you can see here the help provided by the connectivity to the roof. Like it wants to do something like this, but in the midspan, where the Purlin is most flexible, and the roof has the roof clips connected to the roof have a certain stiffness, that the kind of the moment is kind of like taken out of the Purlin. But at the supports, it's not taken out because the supports are much stiffer than the clips. This follows like our intuition about like stiffness and force and moments going to the locations of higher stiffness. But all of that is obtained here, so we can see like where the Purlin is able to like shed moment to the roof, and where it's really got to take it all, and it's taking it all at the supports. This was an interesting result for me. Like I wasn't prepared, I would say, for thinking about like these spikes. And these spikes are a result of the fact that because we're restraining the span along its length because of the roof. Anyway, so we have moments and shear forces. Again, like you can see the shear forces go almost to zero because they're taken out by the lateral springs. But at the supports, you don't get any deformation. So if you don't get any deformation, you don't activate the springs, and so all the force needs to go into the support, and that's what happens. And the same here for torsion. Like the torsion is taken out in the middle of the span, but the torsion builds and collects at the supports, and but we have all of these numbers. One other calculation is the bi moment. The bi moment comes from the torsion, and I'll just so the bi moment, you can think of it like it's typically when we teach it in class, like we think of it as like the bending, the bending of the top flange or the bottom flange, and so that you can think of it that way for a Purlin also. Like the top flange is if you're looking down on the Purlin, it's bending like this, and it's bending like this. It's like bending in the strong axis, I guess, about the strong axis of the flanges. That's pretty much what bi moment is. And so you can see again here that the bi moment really builds and is very high at the supports. And we're not used to dealing with bi moment because we usually aren't able to calculate it. And so like this tests the AISI equations, as I'll show you a little later. All right, so we made it through the deformations and the demands for 10 PSF, and now we can start thinking about like actually running the simulated test to failure, like trying to fail this and determine the gravity load, the expected gravity load. And so the way that we decided to do it was to list out some limit states and to use the AISI equations to define those limit states, like distortional buckling, bending plus torsion, biaxial bending, bending plus shear. Like if you have used the S100 code before, you've seen these. And so we're just using those. There is one new piece, which is this, which we're calling AISI S124. So like this is work that was recently, I think the ballot passed, so this is coming. I would say we're still not quite sure how accurate this is, and we're hoping that other work, like Professor Seek's work, like I've listed that down here below, like so can enlighten us. But like for now, like we have this check on bending plus torsion. And this explains in more detail what that WN was above, and how you can calculate. This is a first yield criterion for the torsion, and that's what. So BN is like a bi-moment capacity defined based on first yielding in the flanges. And remember, this is ASD, so like we're considering the actual the safety factors. Yeah, and other interaction checks. I wrote a couple notes here. Professor Seek is working on a different approach maybe, where you can consider so instead of treating each one of these separately, you could calculate the stresses on the cross section from all of this stuff, all of these internal forces. You can calculate the stress on the cross section, and then run them through the direct strength method equations. And I would say for sure that makes some sense. And so that could be considered here as an alternative to these checks as his work evolves. I would say another key point here that's really important is that, so nowhere have I talked about lateral torsional buckling. I think I haven't even mentioned it yet. And that would be the case here in a typical AISI design. But lateral torsional buckling, in the sense of the code where you calculate like an MCRE, or like you have that equation with J and CW in it that even you maybe all know from hot rolled, like it doesn't. So there's no lateral torsional buckling here. This is like as soon as you start loading, the Purlin starts deflecting, moving, rotating, doing stuff. Like it has torsion on it, like it has a bunch of stuff going, like shears and forces in this direction, and so we don't need to calculate MCRE here. Like we consider the global buckling deformation effects in the demands, in the MX and the MY and the B. And so that's another key point here, is that we have maybe escaped from trying to figure out, like, if you have ever done these checks with like assuming an inflection point at where the moment changes from negative to positive in a negative moment region of a continuous span, like all that. Like, you don't need to do any of that here. Like, it's all considered as part of the interaction check, and I think that's a pretty important point. So let's keep going, and so this is just calculating the Purlin line strength, as the function says, and we get the failure pressure, and we find that the allowable stress expected gravity roof capacity is about 20 psf, which I think is pretty reasonable. I think it turns out to be a pretty reasonable answer. And we can see why it failed. Like, so these are plots. So because we have calculated the demands at lots of points along the Purlin line and the capacities along the Purlin line, we can get the demand to capacity ratios. So like we see here that actually, at least with our current framework, that distortional buckling, the Purlin in gravity fails from distortional buckling out of here at the exterior spans. Because we selected the clip length of 24 inches, so the distortional buckling half wave can form within that 24 inches. Like, one way of potentially improving the capacity would be, and I wrote that down below here, it would be to decrease the clip spacing, to force the distortional buckling half wave to form in a shorter space. But in this case, for these Purlins, the distortional buckling cell is less than 24 inches, and so it can form, and so this is what causes the failure under gravity. And you can see here, like, so there's flexure torsion interaction, and you can see here, like, these peaks, like the cross sections, the Purlin is working very hard over the supports because of the torsion and the bending. And so you can see here, like you can see the addition of the bi moment and the strong axis moment, and how it ends up showing, at least here, that it's working hard. There's biaxial bending, which is not controlling. That's another limit state in AISI. And then there's shear plus flexure, which never controls. And so, yeah, we have predicted the capacity, and also, so because all of this is coded, like you can run a loop and then get you can make these cool plots and study sensitivity. And so, like, this is the tested pressure, let's say, like, or the allowable stress tested pressure, gravity capacity, PSF, versus the lateral stiffness. And also, I'm varying, each one of these colors is also varying the rotational stiffness. So for no rotational stiffness, and for no lateral stiffness, you can see the Purlin capacity is pretty much 0. Well, all right, well, that's pretty good. Like, at least that makes sense. Looks like there's a change in limit state here, and then this comes up, and I think this is probably distortional buckling flattening out. You can see here the sensitivity to the lateral stiffness, the KX. So what I was like, we're right here at 0.1. This is what I assumed. Like for a sliding clip, you probably like in here somewhere, and so you can see how like important the clip stiffness is and getting it right, because you can easily have quite a difference in the predicted capacity. So that's also like an important conclusion here. The plateau here is distortional buckling for large lateral stiffnesses, but you can see all the sensitivity here. Maybe I could have done a better job of like reducing the axes here, but like I find it really interesting here. Like you can even see the sensitivity of just from here to here to here of the rotational stiffness. So you can get a lot of information here. And another one that you can run, and you can run other studies as well. Like I just changed the roof slope, and we're here, our example is here, but if you keep increasing the roof slope, you get a little bit more capacity. And that is, if I were, actually, maybe I can do that now, like as a transition to the uplift loading. Maybe I can ask the audience, like why we get this, why they think we get this increase in capacity, predicted capacity with increasing roof slope. I'll leave that. Maybe people can type something into the chat window, and I'm ready to answer more questions now too.
So Chris, we do have a couple of questions.
Okay.
So the spring stiffnesses that you're using are linear elastic. The question is, have you seen signs of nonlinear behavior in tests for those attachments?
So when I've looked at Professor Seek's rotational stiffness work, and they were linear elastic for a long time, and then they kind of just, it looks like they kind of gave up. So, but that's maybe not such a good answer. So for sure, there's some nonlinearity at some point, and it's not only this. So part of this is now that we have, so well, as we're used to thinking about bracing, we often think about like that you need to have a required stiffness and you have a required strength. And because we have the displacements directly, we know the demands on the demands on the clips. So if we have the K and we know the U, sorry, I'm pointing at the wrong thing, but like if we know the K and we know the U, then we can calculate the force in the clip, and that if we're really designing the clips to carry and help out, like then we should be checking the capacity and the demand and make sure that, as the person asking the question suggests, maybe that we should stay away from the nonlinear range of the fastener. Perform like this, yeah.
And then another
question.
Is the purlin assumed to be connected to the rafter at the bottom flange, or is it connected somewhere else on the member?
So the assumption for the boundary conditions is that the whole cross section is being grabbed hold of. That's like the classical boundary condition. So like all around here, it's being held. So I realize like often there's like a clip that comes down here like this, and that it's bolted. So right now that type of connection is not considered, but that could be included as well as a parameter where there's a discrete rotational spring representing like that type of connection at the location. So the twist fixity would not be fully fixed. It could allow some slight rotation, and that might actually relieve like some of these large bi-moments, like the large torsions and bi-moments that we were seeing. So I hope that was clear.
Yeah, very good. Thanks, Chris. That's all the questions for now.
Okay. So all right, so let's proceed. We're in the home stretch here. Now we're going to run a simulated test for uplift loading. And so now the load is, so for uplift loading, the load is always perpendicular to the roof. And so you'll notice here like that I've drawn that here, and that's how it's included in the analysis. So there's no lateral components considered. We're applying a -10 PSF, and the results are actually pretty well. Oh, one other thing that I should mention is that I changed the KX. So I made the KX half of what it was for the gravity case, because now we're assuming the panel is like being pulled up and it's not hugging here the flange anymore. But the results, the displacement results are pretty similar. Like you see, we get just the uplift deflection of around 3/4 of an inch. Like the rotations are similar, and so like there's nothing. So there's not in the analysis. There's not much difference between for this low slope roof and for the connectivity considered. There's not much difference in the deformation between pulling up and pushing down. Like often we think that there is a big difference, and there might be a bigger difference for simple spans, but for these continuous spans and the conditions considered here, the results are pretty similar, just opposite. And that was actually, I have to admit, like that was a little surprising to me. Again, like I mean, this is the same. I just calculated we calculated the internal moments, and you can see the moments are, everything looks about the same, just opposite signs. And I mean, one key thing here is that the torsion. So there's more torsion in the Purlin, and there's for the uplift case, and there's more torsion in the Purlin for the uplift case because we have assumed that the lateral clip stiffness is half, and so we're assuming that the roof can resist or the roof is restraining the purlin less, and so more torsion builds in the purlin, and so there's less torsion going into, less of the eccentricity effect going into the roof and more going into the purlin. And this is another like really key point that it becomes like very like clearly visible here, is that like changing these clip stiffnesses or clip spacings and types affects how much of the torsion that from the load eccentricity, how much goes into the roof and how much goes into the purlin. And because of that, because the torsions are higher, especially at the supports, you can see the bi-moment spikes even more, like I think it was around here for gravity. When we run the purlin line capacity, we see here, well, first that that this torsional buckling is not controlling now. But what is controlling is some action over the supports. Like, so the flexure plus torsion is just, there's too much torsion in the purlin, and it's just getting worked too much over the frame, and it's starting to like get tired. So this is different. Like again, this is different than what we have, what I would have expected. Like we all think of for an uplift case that the exterior span would go. But I think that there's barely any, I think, uplift tests for multiple spans. Like we'd have to dig around for the simple span uplift tests that I've run. Like for sure the purlin wants to roll sideways. Like it wants to, so this, when you put this piece in compression, it wants to go somewhere. It actually wants to go, it wants to go this way. It wants to buckle this way. But what's interesting is for this uplift case is that the torsion is acting in the other direction. So the torsion is getting the purlin to twist this way, and the flange, the compressed flange, wants to move this way. And so we're seeing that benefit for sure, or we're seeing that interaction. And yeah, so again, like this is, yeah, like we predict that it's flexure plus torsion over the support. I think this is something that we would have to like dig into more. Like, is this, so this could be just the equation that we're using, that flexure plus torsion interaction equation isn't working well, or like we're not characterizing the splice location well, or like we need to soften up, like as that one audience member was suggesting, put a spring here to like to try to soften up the amount of torsion that's being collected at these supports. But this is an interesting result, and it's something maybe like we can't even see in tests where like at that location things are getting worked hard. Yeah, I'm interested to hear reactions from people on if they've seen this in tests, or like, but this is what's predicted with the framework that we provided. And like biaxial bending is not a big deal. Shear plus flexure is not a big deal. So yeah. And I'll just, I made the same plot, sensitivity plot for uplift. It's definitely different than gravity. Maybe not, maybe it's, yeah, it's still, you're right, it's still pretty sensitive in the case of like down here where we may have sliding cliffs. Maybe it's more sensitive to the rotational stiffness. Like I don't remember having this kind of spacing. And also like the plateau is further out. out to, this is distortional buckling, I think way out here when it's held pretty rigidly. But yeah, I mean, these are the results. I think one thing that has misled us when we're thinking about the uplift case is when you calculate the lateral torsional buckling moment for uplift, it's pretty low. But the actual load case, like that MCRE, the lateral torsional buckling moment from this case, it doesn't exist, and it's not even like that close. Like, because you have torsion and the tendency of the lateral torsional buckling acting in opposite directions. It's really, I think it's just not correct, and it's probably like too conservative. Anyway, so those are my reactions to the results, I would say, and I mean, I wrote some conclusions. Maybe I should put an S on this. Yeah, I can do that. I think like a key point here is that Purlin line strength gets a big help from small amounts of lateral stiffness. I think that's all. We've known that, but you can see it here. You have actually numbers, and for sure, like, this could be taken further. Again, rotational stiffness is less important. I'll go through this ongoing work here. Like, so as I mentioned, adding local buckling calculator to this workflow, I think, is important and possible and going to happen. I'll talk a little bit about validation studies, but there's some more validation studies that need to be done. I add pattern loadings and point loadings, add discrete springs that could be used to model intermediate bracing, and also like support points. Like, that's all very possible in this framework. Making this workflow accessible with an API, these days, you could just host this on some remote server and make a call to it and send like, okay, this is my Purlin line. Like, you send it through your browser and it sends back the answer. Like, that's how like Facebook works. It's how like any app we're using works these days, are through APIs. And so all of this could be done with an API, and I'm working on that. Also, increasing calculation speed and efficiency. Like, this is pretty fast once you get everything compiled. But the advantage of these high performance computing languages like Julia, like, they're being used to run millions of simulations for optimization and machine learning studies. And so, like, you can imagine, like, if we're looking to get competitive advantages, like, this kind of platform opens up those opportunities to really like sharpen the pencil. And so, like, there's another level of a few more levels of calculation speed and efficiency that I can take this current work to. And then add 3D visualization and web UI for sure. Like, that's on the list. All right, I'll just talk a little bit about verification studies. I've documented quite a bit here, but overall, like, I've done a fair amount of validation, including finite element, like thin shell finite element studies to verify the deformations that are predicted by the solution of the differential equations. There are some differences and some limitations that I note here, for example, like, so cross-section deformation is not considered, and so, like, if you may get more displacements if you consider cross-sectional deformation along with beam bending. And I've documented, so these open source packages have like a testing log, all of the tests that have run so far to verify things against. I've verified a few things against Mathematica, against Mastan2, and then using Elastina. And all of these, every one of the packages that I've used here today has So for example, like these are the equations from S116 that are currently available that I used. And then I have here like testing some equations, and actually this is for like Bob or somebody, like I need to talk about you. Like the code equations are predicting 9% lower than CFSM, and like I made some notes here, but like so there like this stuff has been like has some formal testing, like that's part of the open source mentality, is that you have unit tests and they're run, and like if it's passing you get this build passing. Like actually I don't know why this one's failing, but like at least I have one passing badge here. And yeah, so yeah, validation is obviously important with these products, and it comes with usage. I think I'll end, and then we can have more questions by just, I wanted to talk a little bit, just have one more slide about open source software. And so like Rick Hawes and others have asked, like, so it seems like there's some excitement about using these open source tools. And Rick has asked me about like how, and others actually, Cara has asked me to like, what can we do? I've been observing other industries like the pharmaceutical industry and how they do it. And what I'm seeing is like open source can be very powerful, but it can also be very messy unless it has to be organized. And so I think that's one key thing that the steel industry could do if we wanted to use open source software more. Open source is not free. Like AISI paid me to do this work. Like this stuff would not exist. And so like, so that's one misnomer I would say, is that like money needs to be available to pay people who know like how to program to get this stuff going. Leadership and structure are important to keep things positive. Like you can imagine you can easily lose control. Like, so you can hear like there are issues and people can get really mean and grumpy and say like, oh, this thing sucks, and like go, you know, like shove it. And like that's not cool. Like so there needs to be there needs to be some leadership and structure around keeping things positive. And what I've also seen watching the pharmaceutical work advancements in simulation is academic and industry support like drives the progress. It's like a combination for sure. And progress is accelerated with software and programming expertise. So like you can the better people you can get who can like optimize and set up structures for like running stuff and getting APIs going, like that is like really a key to where progress meets competitiveness. And so I'll say open source has great potential for increasing steel market competitiveness. And why? Like because you get a lot of smart people working together on building tools for a community. Our community is the cold form steel community, and it's by nature a very collaborative environment. The tools can make design simpler, clearer, more accurate, and automation ready. And that clarity and automation provides new insight that can be used to innovate. Like it's I would say it's that clear. Like, and I can say right now, like building a community, like right now, it's a little bit lonely. I have to admit, I'm out here. I have no stars, no forks, no one watching. No one is looking at this, like using it, and so like so how do we like maybe that means that this isn't important. But if it is important, then we need more people doing this kind of stuff. So I think that's yeah. And who can lead this for CFS? Like, there's lots of people, lots of organizations who could, but if we want to, so yeah, like this. So I've watched. So the pharmaceutical industry is using Julia and open source software, and especially these ODE solvers that we use to solve. Like you can use it to design. You can use ODE solvers to design a roof system, and you can also use it to study drug transport through a human body. And that's what they're doing. And instead of they're trying to replace human and animal testing of new drugs with simulation. And it's really exciting to watch what they're doing. They're investing lots of energy in this, and if you're interested in just exploring what's happening in other industries with open source, you can just click on that link. There is a ton of really interesting and exciting potential. So that's my presentation, and I think we have 10 minutes left, and I'm happy to chat and answer questions.
So we've got a lot of questions here. I'm going to let Bob ask you the questions, then I'll follow up with a closing. Bob?
Sounds good.
All right. So Chris, obviously with this presentation, there's a lot of interest because as indicated by the number of questions we have. So good. That's a good point. First question, is this being modeled as nested sections acting as if they are fully adhered? I've seen evidence of ply separation in tests, especially when you have slotted lap connections. Seems like that would impact the behavior over the support. Again, that's a support topic.
Yeah, support topic is tricky. Pretty much what we did is what most people do, or what I understood from the existing examples. We just, where they overlap, you just add the cross-section properties together. I don't know if that is correct or not, but that's what has been done here. You can see it right here. So you can see here, I'll turn off my webcam. So this is IX 9.18 was for the 7.070, this for the 0.059, and you just add them together. So that's how they were considered here. There for sure could be more thoughtful approach to that.
Along those lines, I think it's sometimes done where you actually reduce the effective length of the lap, which would be another possibility.
Sure.
All right. So another question. What other research do you recommend to support this analysis and design approach?
I think there needs to be, that's a great question. Wow, that's awesome. Can't mess this one up. There needs to be more clip tests, practice on clip tests. Both just individual clips, starting with that, a very basic model like Professor Seek did, or even trying to tease out clip stiffness in, for example, a base test. You can do it, and that kind of thing should be done. There needs to be more work on all of this interaction stuff. So now that we can get torsion by moment, all the moments, everything acting together, what is a good way of actually predicting the capacity when you have those demand loads? I think these interaction equations are it's a pretty traditional way. Mike Seek's working on something, and Shahab and others have worked on other stuff, but that is a key advancement, especially considering torsion, because what we're seeing here is that torsion is limiting the capacity for uplift, and would be limiting for gravity too if I didn't tweak the numbers a little bit, and because we're using a first yield criterion for torsion. So torsion, interaction, and then a new set of tests, like multi-span tests, single span tests, or more tests that are well documented in terms of the behavior of the clip roof interface, the Purlin clip roof interface. So a lot of the traditional base tests, you just apply the pressure and read the number and go home. But really measuring the relative displacements between everything would allow us to verify approaches like this. Great question, thank you.
Okay. All right, another question. I'm going to rephrase this a little bit. But if we look at the uplift case and the results that you got, how would you compare the capacity to that of the current provisions where you where that compression flange is unbraced? How much increase in capacity are we seeing? Is the question.
I don't have I mean, I think there is an increase in capacity. I don't have, so it's like for continuous spans is it 0.7 times my, I think.
I believe so for Z-shape, yeah.
Yeah, I think it's 0.7. I think it's similar, or maybe a little bit higher. I wish I had that. I wish I had that number in my head, but I don't think it's that much different. But the limit state is predicted is totally different. So something is amiss.
Well, what you saw was with sufficient spring stiffness, then it's failing by distortional buckling.
But for uplift, it was failing over the support.
Ah.
Yeah, for uplift, it was failing over the support. It wasn't. Whereas the code equation, well, it's just a multiplier. Like we'd have to go back and look at the test to see how things failed there.
Right. Yep. Okay. Another question. The lateral springs, the KX spring stiffness. The question is, are they externally anchored?
Yes. So that's correct. The formulation is they're grounded springs, continuous springs. So the units of KX in the formulation are like pounds or kips per inch. So it's a distributed spring along the length, and it's grounded. It's not moving, and it's not we assume small deformations in the solution, and so like it's grounded, like it's not doing anything. It's not doing anything fancy, like moving with the cross section, for example.
Okay, well, pretty much wraps it up.
Awesome.
All right, thank you both, Chris and Bob, and also thank you to our participants and questioners. Just a reminder that if you haven't already done it, the handouts are downloadable. Also, there's a link in the chat box to what you're seeing on the screen now in Nextjournal. A couple of upcoming items for CFSEI I want to remind people about. If you go to the CFSEI website at cfsei.org, there is the upcoming Virtual Expo. The 2020 Virtual Expo starts on September 3rd, so next week, continues through November 12th. There are 4 live presentations. I'm going to be giving the first one on September 3rd. And if you register for members, it's only $50. For non-members, it's $200. The difference between the two is actually more than the registration fee. So I encourage people, if you're not a member, to sign up for CFSEI, and then you can attend the webinar for the reduced fee. Also, on October 29th, Bob Gauze, who's been helping out today, will be giving a presentation on demystifying cold form steel torsion analysis for design. So, lots of opportunities for online education during this pandemic. Thank you to everyone for their participation, and we're looking forward to seeing you at next week's webinar or one of these other ones in the 2020 CFSEI Virtual Expo. Everyone, thank you very much. One last reminder that this has been recorded. If you've got others within your association or group that you think may be interested in this topic, please let them know. Also, as Chris mentioned, we need more engagement of industry. We need more funding of industry. If you know of other organizations or associations or individuals that could possibly have interest in funding, there's always an opportunity. So please let the folks at AISI know. So thank you. That concludes today's webinar. We appreciate everyone's participation and hope to see you next week at the CFSEI Online Expo. Goodbye.